No,
What is that?
Guys, let's start. Now, the next chapter, the whole chapter is about circular motion. Okay? This entire chapter is about things that are rotating. Now, there are entire fields of engineering devoted to the idea of rotational mechanics. Okay? Things that are on any sort of rotation all apply to the same laws. My professor that was like my advisor in grad school, his thing was rotational dynamics and rotational kinematics. So he studied anything that was rotating. So for example, like your tires that are rotating on the axle, they would look at the torque. Guys, this way, all heads up this way please, not behind you. They would look at things like the torque that's applied to the axle. If too much torque is applied, it could snap, it could shear. Okay, that's another terminology. If you've ever taken something and turned it up to the point where it snapped, that's shearing. Can you provide a shear force?
Like gas pump, so when you turn it and then it click.
Oh, but that's rotational, absolutely. That wasn't what I was thinking about, but yeah, you're applying a shear force in that direction, absolutely.
What about an Indian burn?
Indian burn, same thing. When you give someone an Indian burn, you're applying a force in two different directions, which applies a shear force between them. A shear force is that rotational force you're going to feel. No, it's not a big deal. Don't worry. It was a date.
Oh my gosh, you turned it
Now, a bullet? I don't know how a bullet's trajectory. Does a bullet spin as it fires? So then it's got circular motion. Absolutely.
Which is why they have rifled the.
Sorry, what? The simple example we could always think of, guys, there are two really, really easy examples. First, think about anything that's like a lasso. If you took something and just spun it around your head like this, no matter what it is, think about like a lasso that a cowboy would actually use, okay? Or if you look at like old medieval TV shows, and you'll see them with these like weapons where there's a ball on each end, and they throw it and it wraps around the person's ankles.
Yeah.
What is that called?
Yesterday.
You know what I'm talking about? There's like a.
There's like some ball thingy at the end.
Yep, that's all it is. There's a circular object on each end. The person whips it around and throws it, and when the other person is running,
It makes you trip.
oops, when the other person is running, it like wraps around their ankles, and then they would fall. They would throw it.
So it's not dangerous?
Okay, it's very dangerous. Yeah. I'm just giving you examples of where circular motion are used. That's all. Another simple one is any sort of amusement ride. Yeah, amusement rides in general. There is always some sort of circular motion. Merry-go-round, Ferris wheel. The one that used to be called the parachute, which was a Ferris wheel at an angle. Think about a roller coaster. Roller coasters, when they loop, it's circular motion. Okay? Circular motion is everywhere.
Are we still gonna go on that field trip? No.
So, you're traveling. Guys, enough. Come on, let's go. It's good discussion when it's amongst all of us, not when it's amongst just two people. Yes. Imagine a person driving north on I-95. Okay, so the person is traveling north. They go to get off an exit. Now, the issue here is this. There are several things. First of all, this is somewhat of a circular track here. Okay, even though we can tell it's clearly not a circle, would be maybe something like that. That's our circle right in there. But the rest of it is kind of off from a circle. But later on, we can call that an ellipse and other shapes. But the idea is that this can be approximated as a circle, so that they can then figure out what the angles needed to tilt on the ramp. Ever go on an exit ramp? The exit ramp is always going to tilt you in, always, because your car naturally wants to move out, and that's called tangential motion. And we'll talk about that in this chapter. Your car always wants to, so say you're turning left on an exit ramp, you're naturally going to feel like you're pulling to the right there, and that's your motion. So the angle of the road is tilted to keep you in. It's like the banked curves in NASCAR. Ever see the guys in NASCAR go around the turns? They're always banked. If those curves weren't banked, they would fly off the track. Like in Final Destination. Now, the idea is that your car can provide a certain amount of frictional force to keep your wheels can provide that to keep your car in motion. If that frictional force is more than your car can compensate for, you will go off the track. So the angle the angle, what that does is it just simply increases the max friction force you can allow. So for example, say you can come back 1,000 newtons on a normal road. When it's banked, your friction force can go up to like 2,000 newtons. So you can go to higher speeds.
Oh, that's why.
Okay, so it keeps you on that motion all the time. Now, there's other things like, your car is lower to the ground and stuff, that's all there too. But the idea of circular motion, okay, it's seen all over the place. It's seen everywhere, whether you realize it or not. I mean, look at a clock. Everybody, look at the clock. It's circular motion. That's all it is.
Oh my
It's an
God.
object rotating.
There's
Okay?
like
It's
years
everywhere.
inside of
I never noticed that.
There it is. I know. It's crazy, isn't it?
The hamster's on a wheel, right? Hamster's on a wheel.
Yeah, sure. Like hamsters on a wheel.
Oh.
How is a hamster on a wheel? The wheel is not the hamster,
I know,
right?
but I'm just saying the hamster on the wheel.
Alright.
Fine, the wheel on the hamster. That's
So
not
let's go
better.
through an
It's not
example.
even really true.
Let's start with an example and think about if we have let's draw a radius with 4 dots on the radius. And we'll show an arrow showing the path of this radius around the circle. So we could say, for example, we can think of this as like an old record player. Okay, with a record player, you would put it down, it would just, depending on where it was, it would have different frequencies of sounds, and the vinyl would actually produce the sound. Now, that location was adjustable if you wanted to go to different songs. So the thing that would read the vinyl or read the record, you could move it based on where you wanted to read the song. Okay? Now it's a laser and it's a CD, so you don't think about this stuff. Now, there is an important thing to think about though. If you put, let's say there's an ant here. So give me a name for an ant, a bug.
Oh,
Pete. All right, so the ant that's sitting here is Pete. One more. Ant.
like a bug?
John.
Oh.
John. All right.
Jacob.
So, because it's a record player, I'm not going to say it's a person. So, Pete the bug is standing here, okay? And John the bug is out here. Now, here's what I want you to think. This spoke, it rotates once completely. So it comes around, so Pete goes in this kind of a motion like that, and Pete gets back to his starting point. Now, John rotates once, but John takes this path. Everybody see the difference so far? Okay. Now, what sort of a conclusion, raising your hand please, can you make about this situation? There's a general one you might see right away.
That the path of John takes is longer.
Very good. So, we'll start by saying the distance traveled by John is greater than the distance traveled by Pete.
They're displacing to 0.
Okay? Absolutely. For both of them, the displacement is 0. Okay? Now, the next thing you want to think about is this. What is the definition? The definition of speed. Of speed. Not velocity, but speed.
Velocity over time. Velocity over time.
Distance by time. Distance by time. Again.
Isn't the absolute value?
So, if we think about this, the distance traveled by John is more than the distance traveled by Pete, correct? So who's going faster then?
The one outside.
We don't know.
John.
Do we really know?
We should know.
The one on the outside is John.
What do you think?
John goes a distance of, let's say, 10. Okay? We'll round to whatever it may
John
be.
goes fast.
Pete goes a distance of, let's say, 4. So who goes further, we said? John, okay? And the definition of speed is just the distance you travel over the time. It takes them the same time to get here because they're on this thing that's rotating like this. So again, the spoke is rotating all together. It's not separate parts.
Going faster?
So in the end, John is actually has a higher speed. So the thing you have to think about is this. The location from the center is indicative of or indicates the speed at which you're traveling. Determines, okay? So the speed you're traveling is a function of the distance you are from the center. As you move further from the center, and you listen to me people, let's go. Come on. As you move further out, your speed increases because you have more distance traveled. Again, the person at the end here would travel the furthest. If there was another bug here, that bug's speed would be in between the other two because of the distance traveled, okay? The distance traveled. In a minute, we'll talk about where we can see an exception, and we'll talk about what's called angular speed or angular velocity. Say out.
Okay, and we're in a minute. Like, we're
Guys, why do you start talking when he's asking? Again, that's rude to him. I talked about this last week already.
like for track races, wouldn't it make it unfair for the person on the winner outside?
Nah.
Because they have to travel, they have to go fast.
So, here's how it works. You wanna start? Go ahead.
Because, with the person on the inside, even though they have like a shorter distance to run, like even though they have a shorter distance to run, since you're on the inside, that's why like with races, like relay races, you see like how they're all positioned at different places.
Oh, yeah.
When you do that.
Exactly right.
That's why.
I never
because
So the inner person travels the shortest distance, as we said. So the inner person starts back here at their starting line. The outer person starts out here, so it compensates for it. They always take that into account. Now, if you go to like a NASCAR race, you start based on your ranking prior to the match for a lot of these. So even like horse races and stuff, if you're the better horse, if you have the higher seed, you get the better starting spot. Because in a horse race, aren't all the horses in the same chamber?
Yeah.
All the horses are in these chambers, the doors all fly open, all these doors fly open, and the horses all shoot out. They're all at the same location, they don't stagger the horses. It's all based on your ranking, so it's a whole different thing. But for track events, for relay races, you're absolutely right, Julian. It's staggered starting points. So this distance here might be 20 meters. Well, the whole distance around for this guy might have been 100 meters, and this guy's might have been 80 meters. So there's the 20-meter difference. Okay, so he does an additional 20 meters to get to that finish line. Now, back to the idea here. The speed of the person on the outside is more than the inside, absolutely. But if we think about angular speed, what is the angle that you've traversed going through a whole circle? How many degrees? 360. Okay, it's all right, 180 semicircle. Now, if both bugs have traveled 360 degrees, and they've taken the same time, they have the same angular velocity. Now, we call angular velocity omega. The angular velocity is the change in the angle over the change in the time. Okay, and we're going to talk about this later in the chapter. It's good that we brought this up, though.
Angular velocity.
Eventually in the class probably, but I don't think it's in this one.
Hold on, you said change in what?
So, this is delta theta, or change in angle,
Return of sine and cosine.
360 over change in time.
Change in angle
Okay, is that big W or little W?
over.
Are we gonna use weight?
That's why I'm gonna ask because
This is a lowercase w. It's a lowercase w.
We're not
Again,
using weight for this.
This is a lowercase w. Okay, we could use weight when we're talking about like friction force on a centripetal track. Okay, lowercase, if it helps, I'll do it like that. Now, it's key to notice that it doesn't matter as a bug where you are on the track there. If you're in the inner track or the outer track, you still go 360 degrees. It does not matter. So the angular velocity for Pete is equal to the angular velocity for John. Again, they have the same angular velocity because they've both gone 360 degrees. But John traveled further. So again, the speed of John, J, is greater than the speed of Pete. Again, the speed of John is greater than the speed of Pete. Okay? So again, let's think about this one last time. John is further out. He travels further, thus his speed is higher because he travels a further distance in the same time period. But they both go an angle of 360 degrees, so they have the same angular velocity. So their angular velocity is the same, but the speed of John is greater than the speed of Pete. Now, this is just an introduction of circular motion that we're going through. Now let's start getting into some mathematical stuff.
What about gears?
Gears do use circular motion, yes. What about?
I'm just thinking.
All right. So the speed of the object that's traveling in a circular motion we define as tangential speed. Tangential. Tangential meaning tangent. Okay? So let's define this term. Tangential
I'm sorry.
speed.
He said tangent, and I was thinking calculus.
So, if we think about an object traveling in a circle, the object's on the out part of the circle right here. The tangential speed, okay, Guys, this is one of those times where the word itself is self-explanatory, so you're going to see it in its own definition, okay?
How do you rush?
Okay, again, you all know what speed is already. Speed is distance over time, so adding the word tangential does not do too much. Here's what we're looking at. We've got an object with a speed that looks like it's tangent to the circle. Remember, when we talked about tangents, in geometry, this was a tangent. Houston, come sit up here. Thank you. I know. Just come sit up here. It's not gonna hurt you. Now, I'm just trying to take distractions away from people around you. So grab that seat where Sales feet are. He's going to move in for you. Now, the speed itself, guys, there's no need to talk while he moves. The speed itself, again, is tangent to the circle. That's the whole key here. If you think back to the example of a lasso, when somebody takes a lasso, I'm looking for one around the room right now, so we can swing it.
Well, why would you have a lasso?
Get on the last
No,
round.
guys, I need someone to throw.
I
Relax.
thought it was just not regular. You want pencil? That's what you put
Like
on
a
your
keychain, your keychain?
Ah, my keychain. There it is. Thank you.
Yeah, that's
By the way,
Thank you, Karen. All right. I need someone I can throw this one. I'm going to throw a belt.
Hey, I got it.
If we think about a keychain, if I were to let go and this keychain was traveling that way, it would probably shoot over at Byron. If I were to let go when the keychain maybe was tangential velocity toward Edgar, it would shoot over to him. If I were to let go when it was going this way, it might shoot over to Mark. If I let go when the key is right on that side of the circle, when the key is on that side of the circle, if I let go, it's going to shoot that way. It's a tangent. So if I let go like that, see what happened?
You wasn't lying.
So as the key was right here in my circle, it traveled that way. It's tangent to the circle. Again. So as I'm spinning this circle, if I let go over here, it's going to travel that way. It's going in this direction. If I let go over here, it travels that way. If I'm spinning it and I let go when it's here, it travels backwards. If I were to let go when it's behind me, it will travel in that
So,
direction.
Mr. Howell, you a good pool player?
I'm a pretty good pool player.
Cause I
Yeah.
was playing pool yesterday, right? And then like my friend was trying to teach, cause it was all about the angle.
That's
Like
correct.
for instance, like don't you know how it's the pockets right here, and then it's the one in the middle, and it was the ball. It was like slightly before it,
Mhm.
and then it was like a little bit the white ball. It was behind it, so when I hit it, it just went. And I was like, I thought it was gonna go in, but then he said you got tilted this way. And when I tilted the little stick this way, when I hit it slightly this way, so it bounced that way.
Yeah, you want to go kiss it. Ever hear that term before? So just kiss it. It means you're just catching the edge of it, so it cuts it at a really sharp angle.
I didn't
See, you know all those markers on the pool table? Ever see those diamonds?
Yeah.
Those are there for a reason. Those are the midpoints of each segment. So on a pool table, when you see that, you're going to see a midpoint here, 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 here. The pockets are all located at the corresponding locations. All these midpoints are used. If your ball is here and you're hitting that ball and the cue ball is here, you want to hit it at a certain angle so that the incoming angle is the same as the outgoing, so it ends in that pocket. So think to yourself, at what angle can I draw this line so that my incoming, like this would not be a good shot right here. That angle doesn't hit the ball. I'd have to move it over a little further to here maybe, so that the angle is exactly the same. So that's my location I want to hit it.
Don't nobody know that means.
And the way the ball moves is momentum.
Oh my goodness, where's my
All right.
That's crazy. I just like, man, I ain't know that knows that deep.
Dude,
Oh, wait.
the equations we learned are there for a reason. Sir, sorry?
Called what?
Ah, you're right. Absolutely right. Spell it B-O-L-O, right? Is that in Spanish, B-O-L-A-S?
Exactly.
In English, they call them bolos. You're right. B-O-L-O. Absolutely. That's what it was. Yeah, guys, the thing that we talked about, you wrap around the ankle, it's a bolo. B-O-L-O in English or bola in Spanish. B-O-L-A. You're right, because the game where you have golf balls and you toss the golf balls, they got a ring on the ladder. Ever seen it before? I'll bring it in. I'll bring it in. It's sweet. I did. It's at home. It's called bolo.
No, we're talking about the dots on the board.
No, we're not
Yes.
talking about that.
Sure. The acceleration is what you do, but where you let it go indicates which
The
direction.
thing that tricks you.
So let's do this.
No. Oh, my, this food you hell. He stole that shirt from Bonnie.
So we got.
You skinned him.
Here's what we want to think about. We want to think about the fact that now we have an object moving in circular motion, but imagine we're looking from above. So I'm standing here with the ring again, spinning it around, but we're above. Now, I want you to understand that right now if I go like this, okay, like this, from looking below, it looks like I'm moving in clockwise motion with the clock. But if I were to look from above, it would look like counterclockwise. So this is what's going on now, me spinning this thing from above. I'm spinning it like this, right? Was that how I spun it? Okay, so watch my hand. As I keep spinning, if I change the angle, still spinning this way. That's how I was spinning it a minute ago. So this is counterclockwise because the clock goes which way? This way, right? So again, you don't have to draw this, but this would be clockwise. Again, that's clockwise. Now, if I let go of the key right here at this point and it's shot this way toward the door, it's shot tangent to the motion. If I were to let it go over here, we said it would have shot toward the whiteboard. Then it would have shot forward toward the whiteboard. Remember, this is the door of the room. Okay, here's the whiteboard. If I were to let it go, as it was behind me, it would have shot toward the projector over here. So if I let it go over here, it's going to shoot in this direction. And finally, if I had let it go on the right side, it would have shot out toward fire. Okay, right toward the back of the room there. Okay, so again, depending on where you let it go, it'll shoot off in any direction. Now, there's an infinite amount of locations because you could pick a spot anywhere in the circle. Pick a spot here, then it shoots off in that tangent. Pick a spot over here, then it shoots off in that tangent. Remember, how do you simply draw a tangent to any circle? Start with the circle, pick a point, and just touch once. Now, when you do that, you only want to use one half of it though. So, if we pick this side, that's the half that maybe we care about if it's motion. Let's say the motion is like this, but this is the other half of the tangent, really. You don't have to draw the other half of the tangent though. So that dashed line you don't need every time you draw these tangents. So again, a tangent is always as if there's a dashed line back here, okay, but that dashed line does not matter because we're looking at the direction of motion here. We clear on this? Okay. Let's go through a quick formula.
Hey, you find it outside.
All right.
He's calling you.
Just by me saying it, I feel like I can see it.
I'm not even back there and they still talk about me. I'm in the front now.
For centripetal acceleration, the idea of acceleration, again, is a change in velocity. It's a change in velocity. Now, the hard part to remember right now is this.
Confused your teachers talking like that.
Remember, here's what I want you to look at. At each of these locations, the object might have the same speed. Again, at each location, the speed might be identical. But the speed is pointing in a different direction every time. And if you remember, velocity is defined as a speed but with a direction as well. It's a vector. A vector, remember, has a magnitude and a direction. So, the key point you want to notice is this. The direction of the speed is always changing. If you ever change the direction of speed, you must have a changing velocity. Okay? So, let's call this A, call that B, call that C. The speed at A is equal to the speed at B, which equals the speed at C. It's not changing the speed.
Didn't we do that?
Okay? But the direction of the speed is changing constantly. So the velocity must constantly be changing. So the velocity at A, its absolute value might be the same as the other one, so it's the same velocity or the same speed or magnitude of it, but it's always changing direction. It's constantly changing direction. So the velocity at A does not equal the velocity at B, which does not equal the velocity at C. And this is the weirdest thing in the world to think about, because a minute ago we said the speeds are the same. The velocities are not. If you take, as Isael said, or Kenny said a minute ago, the absolute value of the velocity, if you take the absolute value, then you can say it's true. So you could say this.
Because you're saying that velocity is because of different because of
I get it. I get it.
magnitude.
Because of the direction, not the magnitude. Again,
There's
let's discuss. Watch what happens here. Call this
Because directional, right?
10 meters per second north
northwest.
for A, north for A, guys, for A.
No.
No, for that be northwest.
Oh, okay, not there yet. 10 meters per second northwest, thank you, and this would be
Southwest.
Oh my God.
southwest.
Yeah, southwest.
Now, we can see already, every one of these is 10. If they're all 10, then they have the same speed because they're all 10, that's fine. But the direction changes. That's why the second line is there. That's why the velocities aren't the same. So remember, the major difference between velocity and speed is velocity has a directional. So the directionals are not the same. That's why these are not equivalent here. But, these are all equivalent to one another because the absolute values are the same. The absolute values are literally the number. The absolute value tells you to drop the directional. When you take the absolute value of these three, it's saying cover up the southwest or cover up the northwest. And you see 10 meters per second. We're saying that they're all the same, the numbers, okay? Again though, notice that velocity has to have a direction, so these three are actually all going to be different. But their absolute values are all the same. Kenny?
Well, I was gonna ask you that, like, when solving equations having to do with like centrifugal acceleration, would they tell you if it's like if you take the absolute value of it, and what would you need to, like?
No, it's not going to come into play. It's not going to come into play because in a minute we're going to discuss where centripetal acceleration goes and how that works. And you'll notice that it actually doesn't matter. Give me a second to answer your question that way. So, who, you guys all, did everybody take Latin or some people take Spanish?
I took Latin.
Everybody took Latin?
I took both.
So, use your clues of etymology and breaking down words. Centripetal, center,
Try.
Is it like
center seeking. Okay, center seeking, that's what it means.
So.
Now, let's discuss for a second why this actually makes sense. Let's discuss now why this actually makes sense
Center
here.
seeking.
It's going to be very, very complex here, so just watch my diagram. Don't draw anything yet. I'll give you a minute to draw it afterward. Just please watch. So, let's say we're looking at a particle that's in circular motion, but we're only looking at the arc on the top. So this object continues in a circle forever. Don't draw yet, just watch please. I'll let you draw in a minute. Please watch. So first the object is here, then the object is here. The velocity at the first point is that direction. Okay, the velocity at the next point is that direction. Guys, listen for a reason. Don't talk, listen. Just listen for now. Now, if I know that this was the velocity before, so like we'll say at time 1 or initial, we're looking only from here to here, and we'll call this final.
Now I'm confused.
Okay.
You said it's the same thing?
It's the same object, we're spinning it, but we're looking at 2 points in time. So this is initially, we take a picture, and we have the object there,
Click.
and we're able to see that there's a vector, you can't really see that. Then we take another picture of the object here,
Click.
okay? So this is the initial velocity, this is the final velocity. Now, our definition of acceleration, remember, to be delta v over t. Okay, that's our definition of acceleration. So the question becomes this. I want to isolate delta v. Well, delta v is really vf minus vi. Agreed? Okay, still watching, guys, still watching. Again, I'll put a little line here to show you where I'm adding. So that's what you're going to have to write after it. Delta V is going to be your VF minus your VI. Now, if I want to draw that, how can I indicate subtraction with vectors? Do you remember how we added vectors with tip to tail? And we lined up one vector with the other vector, one after the other?
Is it tail to tip?
Okay.
Is it tail to tip? You put them in opposite directions.
Very good. That's exactly right. So here's what we want to do.
Oh.
Listen carefully, guys. This is confusing. Come on. If you want to figure out what VF minus VI is, think about it this way. VF plus negative VI. Again, when you subtract two things, it's like adding the opposite, isn't it? Remember? If you add a negative, it's the same thing as subtracting. So if I want to add the VF vector, I take the VF vector and put it like this. I draw it to start. Normally, if I wanted to add VI to it, I would just add VI like this, and then draw the resultant like we did. We did this in chapter 1. But I don't want to add VI. What do I want to do to it? I want to subtract it, or I want to add the negative value of VI here. So instead of going up, I go back down. Now watch this. Okay? So again, this is VF. This is the negative VI here. Now watch what happens. This is the cool part. If you start at your starting point and go to your total final point, which way is this directed with regards to the circle? To the circle.
South.
South. And it was on the top of the circle, right? So isn't it directed toward the center? Again, look, this is your acceleration vector, or your, so this is not really, this is your delta V vector here, which becomes acceleration. This is directed down when it's toward the top, which means it's directed toward the center.
But if you look at it,
Okay? If you do it on the side, you'll get the same answer. It'll be directed left.
Yeah.
If you do it at the bottom,
Circular.
it'll be directed upward. So, our idea of centripetal acceleration really is center seeking. The acceleration vector is always drawn toward the center. No matter where you are, if you take 2 points over here, and you were to add those vectors together, you would have this one going like this, you would have this one going in the negative direction back up, and then you would see your acceleration vector, again, is directed toward the center. So no matter what point you're at, again, this was your VF here, that's this direction. This is your VI, so negative VI would be up that way. So VF minus VI, and there's your delta V, or your acceleration. It's just a proof of where it comes from, okay? I'll give you a minute if you want to draw whatever you'd like to. But the idea is that it really is directed toward the center.
Understood.
The acceleration really is directed toward the center.
So did you see my face when you moved? Yeah, John.
I ain't nobody getting Cowboys for later.
It is pretty cool stuff, guys. It's important to understand, I'll make sure.
It's cool when you understand my problem.
You look like the great player.
Still fall more than you.
You look like Raji.
Raji.
No, the idea is that so like an electron goes around orbit, how is it going to nuclear force?
Rename who? Discount double check. Discount double check.
I mean, if it was full,
I know it's weird. It's really weird.
So who, I used to do what?
All right.
Well, who used to work?
I think I get it.
I don't know what you're talking about. I would've got it hit.
So the idea here is this again, guys. The acceleration is directed toward the center. It's always directed toward the center. That's got to be like at the end of this unit. That's one of those things that's got to be second nature. Okay. Acceleration directed toward the center. Now, if you want to write down, let's start at the next page. The formula for centripetal acceleration, which you don't have to memorize, I'll give this to you again, is going to be your tangential speed over r. Okay, your tangential speed squared over r. Now, we could also write this as follows, if you'd like to. Okay, and that's the way you see it normally on the right here.
What's the T for?
Again, tangential T.
R is for radius.
Okay, people, let's listen, because I said all these already. Let's try one more time and listen carefully. Please don't ask this question again. AC is centripetal acceleration. Okay, the T indicates tangential. I've said it 3 times now. We need to all listen and stop talking here. Now, it's speed squared over r. But again, speed is the absolute value of velocity. This is the one that you see more often. And a lot of the time you will even see it written like this. Okay, which is really not correct. Okay, it should really have absolute value around it, and we should really indicate the C and the T. So I would like you guys to remember it again like this, please. Okay, it's very important that you understand the difference, because without that absolute value, you're then saying to yourself, okay, well, we're now looking at the velocity, but it's not true. It's really the speed that we're looking at. It's the speed.
So it doesn't matter, what that's basically saying, it doesn't matter about the little negative sign. You don't need the negative sign.
Correct, correct. Absolutely correct. What does T stand for? Tangential. That's 4. Now, if you guys want to remember this, here's an easy way to think about it. If you start applying negative signs here, okay, the only time you're ever going to have a negative sign for acceleration just depends on the direction you're going clockwise and counterclockwise. So for the sake of our class, here's what I want you to remember. This is for the rest of the year, and we're going to use this several times. We're going to call clockwise to be positive, okay, and we're going to consider counterclockwise to be negative. So if an object is moving in a clockwise manner, its acceleration will be positive.
Okay, so clockwise and counterclockwise.
Okay, again, so if the object is moving in this motion, its acceleration is considered to be positive. If it's moving in the counterclockwise direction, think of it as negative. Okay? Again, we all know though, where is our acceleration really directed?
To the center.
To the center, thus centripetal acceleration. Okay, thus centripetal acceleration. Last thing, and then we'll look at a problem. All we need to look at now is our centripetal force. Okay.
Oh, hold up. There's a difference between the centripetal force and acceleration?
Okay. Now here's the hardest part. Can you focus up here, please? Here's the hardest part for this problem. You get distracted. Come on. For force, we always think about something that's really tangible, right? So like if I push on this desk, I'm applying a force. The desk is pushing back up on you because you're sitting on it. It's a normal force. It's something that's actually being applied. Whereas circular motion sometimes can be very misleading. Let's look at 3 examples before we actually define force. First example, the key that I was spinning. The key that I was spinning here. What is keeping this key from shooting off track? My hand. Good. Now between my hand and the object itself, what is here? What is this? A string or a rope. What is it?
Tension.
Tension. Tension. So, if we have a key,
Got that?
if we have a key spinning, okay, or anything spinning on a rope, any rope whatsoever, okay, the tension, the centripetal force is the force of tension. Next, Adolfo, if a car is going around a track like in NASCAR, what provides the centripetal force there? Friction between the car and the road, or sorry, the tire and the road. The tire and the road. So, about a car in circular motion. What provides the force to keep it in the motion is friction. Force of friction. Now, here's an even crazier one, and I know I just told you don't answer this one. What about an electron in orbit? What keeps an electron in orbit?
The nucleus. What you call it?
Magnetic force.
The
Gravity.
negative charge?
The negative positive charge. Okay, the negative positive charge. So we could say the nuclear force or the electromagnetic force. Okay, but we're just going to say some sort of electromagnetic force in general. Okay, so let's say electron in orbit. Okay, it's a type of electromagnetic force. So this is where it gets difficult because can you see that force?
No.
You can't see the force that holds an electron in orbit. You physically can't see it. So here, you can't see this force either, really. I mean, you see the tires, but you don't see any force. But with the tension, you can see the tension in the road. Everybody can see that the rope is what's holding it there. That is there. The tires, not as much. This one, you can't see at all. Now, the centripetal force is not a new force. It's a force that keeps something in circular motion. Keeps an object in circular motion. Yes, the Jedi's can. Keep an object in circular motion.
What the EM stand for?
Electromagnetic. Electromagnetic.
Hey, what did I say? Hey, what?
Keeps an object in circular motion. Okay, keeps an object in circular. So, here's the hardest part about circular motion that most students confuse. This centripetal force is not an actual force or a new thing. It is just every situation you have a different centripetal force. So again, when the key is spinning, tension is the centripetal force. When the car is going around the track, friction is the force. When the electron is in the nucleus, the electromagnetic force is the centripetal force. Now, it's all about free body diagrams. Okay? You can balance your forces. That's where this all comes from. Now, if we want to define this, let's quickly define it analytically or mathematically. We said a minute ago that acceleration was defined as Vt squared over r, where Vt was in the absolute value. So if we want to think about force now, it's the simplest derivation you'll do all year. Start with F equals ma. Then say, well, force, okay? So centripetal force equals mass times centripetal acceleration. I'm just calling them both centripetal.
Just add that.
Now, take this next thing and replace it in AC. So centripetal force is really m times Vt squared over r. Okay? Fine. That's work equals FP. Okay? So, again, this is your acceleration in circular motion. This is the force that is felt by the string. So if you know the mass of the key, and you know the tangential speed, and you know the radius or the length of the string, you can find the force that is being pulled on the string. And in turn, the force that you need to provide to keep it in motion. We're going to do a lab where you guys are going to actually spin a bunch of stuff and be able to determine this.
Can they please have cushions at the end? 'Cause, like, can they have cushions at the end? Because, like, everybody...
You'll be fine, don't worry guys, it won't hurt. Too much.
Right?
Trust me, you'll be fine. Let's listen to our questions. Christian and Taysir, please. Christian? Tangential velocity. Taysir? Where are you at? Here? R. Okay? So, now, here's what I'm going to tell you. On your test for this chapter, I'm going to give you this formula here. I am not going to give you this formula. Okay? You don't need it. You have F equals ma. If you take this expression and put it into A, you get this formula. Okay? Again, this is given on your test. This is given on your test. These are not going to be given. Okay? You know this already. This is always F equals ma, Newton's second law. You know acceleration now. It's going to be given. Plug it in for acceleration. That's where the force comes from. I want you to understand where it comes from. Please don't memorize this. If you know these two, you know this one by default. All right. Let's do one problem before we end. Please write, people. If the radius of motion of an object in circular motion is doubled what happens to the force. Okay? You know what? I promised you I'd go over the test. Think about this tonight. Try this tonight. We have 1 minute left. Yeah, 12:09, the period ends today. Okay? So here's what you're going to do. You're going to take your score that you see on your paper. You're going to add 6 points to it before you divide. So for example, if you had a 25 out of 43, it is a 31 out of 43. That's your actual grade. Do you understand? Everybody clear? Now, there are a lot of mistakes, a lot of silly mistakes along the way, so please look at this beforehand. I'll post the solution online on Endline tonight, so you can read through the solution if you have any questions. The highest grade was a 37 out of 43, which makes the highest grade a 43 out of 43.
It was Houston?
Okay, it was Karen and Star. Okay? Two people that came for extra help a lot, and also we did a lot of extra problems, guys. Take a hint by that. There were a lot of people in the 30s and there were a lot of people in the 20s. There were a few in the teens.
At the same time, I might have said two.
This here. Terrence. Bart. Add 6 to the numerator and then divide by 43. Isael.
Wait, will you second?
Kenny.
Oh, that's a
Add 6,
blow.
please.
No.
Tony.
We're just not here. It's up. Again, I'll post the solution on Headline tonight.
Karen, we all know you got it.